Crying, crying. Wah. Last problem, people. The last one of said course. Love. All right. Here we go. This problem says, calculate the EMF, the voltage, of the following cell battery. Okay, because calculate the voltage produced by this battery. This is an interesting one. I liked it. That's why I did this one. I like that. I like that. I like that. I like it. It's cool, 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 cool. You have magnesium connecting up with magnesium. Now you might say, that doesn't make any sense. We've always had a metal and a different metal. Correct. This time we got a metal and the same metal. Well, a metal and the same metal, you would think, shouldn't produce any voltage, because if we look on the chart and find magnesium on here, it's down near the bottom, which means it really wants to be oxidized. It wants to give away its electrons. Negative 2.37. So if I have magnesium and magnesium, that would be magnesium at the anode minus magnesium at the cathode minus magnesium at the anode, 2.37 minus 2.37 is 0. I get no voltage because you don't have any differences between the metals, so you shouldn't get any voltage. Correct, absolutely correct. Oh, so problem's done. The answer is 0. Then we get no voltage. No, wrong, We have different concentrations of the magnesium solutions. So one concentration is 0.24, one is 0.53. So one is more than twice as concentrated. That means nature doesn't like things unbalanced, so there would be a shift until we get balance in the force look. And while that shifting is happening, we are going to produce some voltage. We have flowage, we have electrons moving, that's electricity, we have voltage. All right, now, since we don't have 1 molar solutions, we have to use the Nernst equation. The Nernst equation. All right, let's do it. So, E is equal to, oh, that's not 0.13. That was from the last problem. Get rid of that, you silly, you silly. So silly. I'm losing it. Okay. So what are we going to put here? Well, let's do the E of the cell. Let's do it. E of the cell under standard conditions would be E at the cathode minus E at the anode. And that's negative 2.37. Okay. Verify that because I think I remember. Yeah, I remember. 2.37 minus negative 2.37. That's plus positive. That's 0. Which, under standard conditions, everything being equal, it should be. So that's a 0. All right. That part done. Okay, this divided by 2, there are 2 electrons being exchanged, hence the 0 to positive 2 or positive 0, 2 electrons being exchanged. Put a 2 in there just like last time. So that's a 2. Oh, I left it in from last time anyway, so there it is. Okay, and then so this, if I remember right from last time, was 0.018. Is that right? Brain hurting brain. 0.01285. 0.01285. Okay, so take that, divide it by 2. 0.01285. Okay, that was from last time as well. Whew, cranking through this. Now, we need to get a Q expression. Okay, so we have to write the reaction out. We still have to write the reaction for what's taking place here. Now, this is standard galvanic cell, electrochemical cell notation, which remember from the uranium problem, not my uranium, your uranium. It tells me who's being oxidized and who's being reduced. This one's undergoing oxidation, 0 to plus 2. This one's undergoing reduction, plus 2 to 0. So this one here, magnesium, okay, that is my oxidation. My reduction, 2 to 0. Okay, there's the reaction. That's what it's going to look like. And you might say, well, it looks the same on both sides. What difference does it make? What matters, remember, what matters is the concentrations aren't the same. So this Mg is only in, so this Mg positive in solution here is only 0.24. This Mg positive in solution here is 0.53. So they're the same, yet different. Well, what would my Q expression look like then? Q is products products. So the concentration of Mg2 positive. Put in the Mg solid, right? No, it doesn't go in the Q or K expression. So no, don't need it. Over Mg2 positive ion in solution times that Mg, again, doesn't go in because it's solid Mg, you don't put those in. So it's Mg2 positive over Mg2 positive. Oh, well, that just cancels out. That becomes a 1, and we'll do the math. No, no. This Mg was the product of oxidation. Remember, this became oxidized. This became oxidized. This one is 0.24. Okay? That 0.24 goes on top. Now you have a 50-50 shot at it. You can put the 0.24 or the 0.53 or the 0.53 or the 0.24. You have the 50-50 shot at it, go for it. But no, we don't want to go for it. Let's get it right. So this one here went from oxidized to magnesium. So this one here went from here to this one. So this one here on the left, the reactant is 0.53. And the reactant goes on the bottom, 0.53. Okay, so that, actually I'm doing the Q value thing right here. I'm doing that out now. So the Q is 0.24 divided by 0.53. We got that, we got that, we got it, got it, we got it, it's 0.453. So this comes out to be 0.453. So that Q is 0.453. There's your expression. Some of it's already done out for you. So let's go ahead and crank that out. Okay, get rid of this now. Bye. I guess we can get rid of you. We don't need you either. We don't need you. We're done with you. Get out. Get out. We don't need you anymore. We use you like a tool. Yeah, I am losing it. Okay. All right, so natural log of that. Hit it. You get negative 0.79. Negative 0.79. So E equals 0 minus 0.01285 times, okay, negative 0.079. Now, this is a 0 minus a, this is going to be a negative value. When you get this product here, you multiply, you get a negative x. Subtract the negative, gives you a positive. Gives you positive. So you are going to get some voltage out of it. It makes sense. Positive, you get some voltage. Not a lot. There won't be a lot. Okay, they're weak solutions of the same metal, so it should not be a big number. But if I do this out, negative and negative is positive, multiply those two, you should get 0.01015. 0.01 volts, essentially. Not very many volts. Not exactly going to be powering your calculator or your cell phone, but it does work. It does produce a little bit of voltage. Okay, folks, that makes like a gift and wraps up the problems for the course. I was crying on the inside, deep down, crying.